Hi there, I'm Hao. This is just another video of me solving random code problem. So given an n by n binary matrix, MAT, MAT, return a distance of the nearest zero for each cell. And the distance between two adjacent cells is one. Right, so like the distance between from 0 to 0 is 0, right? This is already a 0, right? And the distance of this one, right, from 0 is 1. Same for here, right? The, this 3, right, is only one step away, one cell away from the 0, but this one will be 2, right? So that's why we have 1, 2, 1 here, right? 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 2, 1, right? Which is the result here. Okay. So we can use because they're talking about the nearest distance, right? So it's a very good thing that we should use the breadth first search, right? If you think about it in terms of a tree, then it will be something like this. Like you start from like let's say we have 3, 0, right? 3, 4, 5, 5, 0 here. 1, 2, 3, 4, 5, right? And then we just start from the 0, and then look at the neighbors, right? The neighbors that is like not visited, right? So if like this one, look at this neighbor, so those are 0, so it doesn't count, or it's visited. Right? But if you look at this neighbor, right, in this 1 and 1 here, right, you can set the. So imagine like this cell is empty, no value for the cell that is non-zero, right? So we can set like the value for this cell to be +1, right? +1 to 1 and 1, right? 1 and 1. And then what is this? This one is here. Instead of doing the 0, it's a little bit hard to imagine. Let me just write out the index here, the index here. So 0, 1, 0, 2, 1, 0, and 1, 2, right? And then this would be what? Would be 0, 0 is have no valid neighbors. 0, 1, 1 neighbors, right? So this is 1, 1, right? Let's become 1 +1, right? Uh, 0, right? Oh, 0, 2. Oops. 0, 2, no valid neighbors, right? 1, 0, 1, 0 is 2 valid neighbor, right? 1, 1, we already look at 1, 1. So we'll look at 2, 0 here, right? It is also +1. And then 1, 2. 1, 2 have 2 valid neighbor, right? Which is 1, 1. We already look at 1. We look at 2, 2. So it is also +1. So this is the level, right? Level 0, right? Level 1, 0, level 1, level 2, and then level 2, we just keep going, right? 1, 1, we can look at the 1, 2 here, right? Sorry, 1, 1, we have 4 neighbors, right? But 3 of them is 0. The last one is 2, 1, which is a valid one, right? So we +1 here, right? Similarly, 2, 0, there's no valid neighbor, right? Because 2, 1 we already visited. Same for this one, right? So this is like 3 levels, right? And yeah, we can just return back up, right? Um for the value, right? So doing it this way, which means that um yes, which means that we are doing the breadth first search, right? For each node, we start from the 0, and then we look at the neighbors of all the zeros, right? Which is these 3, right? This is our next level, and then we iterate through the level, sorry, all of the node on this level, and then look at all of the neighbors and just keep going like that, right? So how can we do this in code? So we can set the value of each node that is non-zero to be like -1 or no, or just like anything, just for the placeholder, right? Because if we don't, um, if we don't, then we need to keep track of a visitor set, right? Because we don't know if we have visit that node or not, right? Um, so let's say we start from the zero, right? And we do 0 plus 1, and we set this node to 1, right? This node to 1, uh, just to 1, and this node is also to 1, right? So in our next iteration, right, we will look at the neighbor of these three yellow, right? And the value is also 1. So we don't know whether or not we have already processed it or not, right? Because the values might be duplicate. And if we look at the constraint here, the math of I and J will only be 0 or 1, right? So we can just set like the node, the unprocessed node to -1. So that is our strategy here, right? So let's look at an example. Well, for the 0, we don't do anything, right? So the whole reason that we set it to -1 is just to save some space, so we don't have to use a set to keep track of the visited node. So it would be -1, right? -1, -1, -1, right? So remember, what is our first level? Our first level is 0, right? We iterating to every single 0. The first one, like no valid neighbors, right? The 0 here, there's one valid neighbor. So the valid neighbor now means that it is a -1, right? If it is a -1, then we process it, right? Equal to 0 plus 1, which is 1, right? 1. This one have no valid neighbors. This one have two valid neighbors, right? But we already processed this one. We only look at the -1 here, right? So become 1, right? And then the next 0 here, right, is have two valid three neighbors. This one we already processed. This one is 0. So we set this node to 1. Okay. Okay, now we are finished with the first level, right? So the next level, we look at one by one, right? This node first. It does had 4 neighbors, but 3 of them is 0, right? Only one of them is -1. So we process that equal to the current value plus 1, which is 2, right? Same for here. We look at this node, no valid neighbors, right? So we can return. So doing this, we can do this in constant space. The time complexity would be over n by n, right? Because you only process each node once. All right. So let's code this up. As always, I want to start by creating some constant. So we want to iterate through each node, right? The whole matrix to set the node that is non-zero, to set the non-zero node to -1. So we know like that they haven't been processed yet. So row equal to 0, row is less than row plus plus, then for column. So if the math row column is equal to 0, we do something, right? Else we set it to -1. Okay. So we want to keep track of the starting node, right? Q equal to here an array. You can do Q dot push the row and column, right? So we can do Y Q dot length, right? So this step we do two things. We keep track of the 0 location for the starting point, our starting point of the breadth first search, right? And the second thing is to set the non-zero node to -1. Okay, and we can return that at the end because we are doing it in place. The only space complexity that we have is the Q here, right? Which is O of m by n, in case like every single node is a 0. Okay. What do we do here? We want to look at the row and column, right? So Q shift. We also want to look at the current value. Current value equal to add a row and a column. Okay, so what do we want to do? We look at each 0, right? Yes, and for each node, we want to look at their neighbors and set the neighbors to the current value +1, right? So we need to look at the neighbors. So neighbors at row and column, not for each. New row, new column. Right? And we want to set the mat of new row, new column to 1. Oh no, to not 1, to +1, like current value +1. And we only want to do it if what? If the neighbors is -1, right? As I said earlier. Right. We set the value and then we need to add them into our queue, right? We can queue push new row and then new column, right? So that we can process this node as in our next like level. Okay. And we need to create a neighbors method. Returns neighbors taking the row and the column, right? And then return a pretty array of the neighbors. Row column -1, then row, then column +1. Right, and we want to filter to make sure that they are in bound, right? Which is new row, column, to make sure that the new row is not negative, new column is not negative, and it has to be less than rows, and then new column is less than column. Okay, and that's pretty much it. Give it a try. Grid is not defined. Yeah, of course, grid, math. I was using grid too often here. So okay, it is accepted. Okay, but the the time complexity here is not O n by n now because we use a queue, right? As an array as a queue here. So the sheaf would like reassign the indices. So that we O of n by n square, right? In JavaScript, there's no built-in queue. If you use another language that have the built-in queue, we use it. I'm just gonna use like queue class that I have built here. I'm not gonna go into it, but we're just gonna have the NQ and DQ here. And we implement it using a hash map. Okay, so let's run it again. Oh, and we need to update, right, to use our queue. Instead of push, we have MQ, right? And instead of shift, we have DQ. DQ. Run again. Make sure it works. And then submit. And thank you for watching.